So in the last part, we got up to here, right? Rate of change of heat energy is the heat flowing across the boundaries per unit time, plus heat energy generated inside the volume per unit time. Okay. So in this next part, what we're going to do is rewrite things, rearrange things. The main thing that needs to be rewritten is that. Move things around, use a version of Fourier's law of heat conduction, and then recover kind of the heat equation that we're after. Okay. So the key kind of tool to rewrite everything is the divergence theorem. If you don't recall, divergence theorem says, well, what is the total flux over the boundary of a region? We can either compute it as the surface integral, right, the boundary of our region, or we can compute the same quantity as this integral over the interior of the region. What are we integrating? Well, we're integrating the divergence of the vector field. Okay. Roughly speaking, how the proof goes is you consider this quantity and then you realize, well, the only things that really matter are kind of the divergence across the boundaries, and that's exactly this term. Okay, of course, there are more details, more is involved, but that's the, I don't know, quick description. Okay, but this is going to be our main tool in deriving the heat equation in higher dimensions. Okay, so we have this divergence theorem. So what do we have? So this is what was written above. Okay. And so the next step is, right, well, move this derivative inside, but also take this term here, right, which is exactly that term there, and replace it with this term, which the divergence theorem tells us we can do. Okay. So if we do that, we get something like that, okay, plus the source term. And so now everything's with respect to kind of the same bounds of integration, or the same region of integration, right? We're working with 3 volume integrals of the same region. So what we can do, move everything to one side, bring everything under the same integral sign, and we get an expression like that. Okay, which is very close to the heat equation in one dimension. Okay, we have, right, this term, which is the same, this term, which is the same. And now instead of the x derivative of the flux, x derivative of the flux, now we're working with the divergence of the flux. Okay. So the observation, right, similar observation as in one dimension, is that this is true for any region R. Okay. So the fact that, right, if you integrate this function right here, and assuming this function is nice enough, if you integrate this function over any arbitrary region R, right, make R as large as you want, make it a cube, make it as small as you want, have at it. The claim is that if this condition holds, then the only possibility is that this function here is 0. Okay. And that's what's written right there. And then rearrange things, we get something that's close to, right, the final heat equation. So, right, the only thing that's kind of missing is an interpretation, or maybe a rewriting what this divergence term is. Okay. So the question is, well, what about this divergence term? Can we express this in terms of, say, the temperature? As you might have guessed, the answer is, well, yes, because Fourier's law still holds. Okay. What was Fourier's law? Well, the flux for temperature is proportional to the gradient of temperature. Okay. So this is the law written out mathematically. What are these? What are the interpretations of these pieces? Well, this gradient is saying that term, right? This gradient term is saying that whatever this flux is, right, or this flow, is proportional to kind of the temperature difference or the temperature gradient. Okay. We have a term that just depends on the material. Different materials may let heat energy flow through them different rates. And finally, we have this minus sign, which tells us that the flow is from hot to cold. Okay, heat wants to, or energy wants to flow from regions of higher temperature to lower temperature. Okay. Okay, so plugging that in, right? So this was the expression that we had above. Plugging in Fourier's law for here gives us this expression. Okay, and of course, simplifying it, right, removing the negatives. So removing the negatives as well as rewriting it maybe in more English, or kind of the names of these operators, we recover the heat equation in this case, 3 dimensions. And so you may be wondering, well, does it also hold in 2 dimensions? It does, and we'll touch on that in a second. Okay, but this is what we were after: heat equation in 3D. So as I mentioned, this equation also holds in 2 dimensions. Why, you may ask? Well, the divergence theorem also holds in 2D. Okay, so just copying the pieces over, this is what the divergence theorem says. Okay, what is the total divergence of a vector field over a 2-dimensional region R? Well, that's going to be the flux across the boundary. So this is flux, this is the boundary term, B is going to be the boundary of the region R. Okay. And so we'll stop there.